Alright, this example is example number 312 of the book, and it involves solving this circuit and finding Ix and Vx using node voltage analysis. And because there is a super node in this circuit, and the concept of super node is one of the most confusing things for students in my experience, I thought I would make a video about this example. Hopefully it makes things easier. So I have a 15 volt voltage with this polarity, 500 ohms, and all this other components. So these are all in kilo ohm. The only one that is given in ohm is this 500 ohm one. So I changed it to avoid making mistakes. I changed this to 0.5 kilo ohm. Alright, now the first step in doing node voltage analysis is to specifying one node as my ground. So I assume this lower node, this bottom node, is my ground here. Then I label these three other node voltages: VA, VB, and VC. So the next step in node voltage analysis is to write KCLs for each node with an unknown voltage. I notice here that my VA is known because I have a 15 volt connected between this node A and the ground. So VA minus the ground is, be careful about this polarity, it is minus 15. So VA in this example is minus 15 volts. But VB and VC are unknown, so I have to write KCLs for them. So I can label this current I1, this current I2, this current I3, this current I4, and this is already Ix, so I will use this here. But I notice one problem here. When I try to write the KCL at this node, which will be I1 enters the node, I3 and I2 leave. The next step would be to express all the currents in terms of node voltages. So I1 is VA minus VB over 0.5K, I3 is VB over 1.5K, and I2 is what? VB minus VC over what? What's the resistance? So I cannot write I2 in terms of node voltages because of this voltage source here between two nodes. So I don't know what to do here. So it doesn't work this way. So in this case, because we have a voltage source, ideal voltage source between two general nodes of the circuit, I need to create a super node here. And somebody at this point may take, okay, if I have assumed this is my ground, if I think my ground is here, my B is, the node B is my ground, does it help? Does it help avoiding a super node? So if I make this my ground here, I notice that, no, alright, now VB is my ground. So I know VC, right? My VC is minus 10 in this case because this is my ground now. However, I still have another voltage source between this node and this bottom node. So I will still have to create a super node here. So changing the ground in this example, in this problem, doesn't help. It might help in another problem, but not here. So I stick to my first assumption. I still specify this bottom node as my ground and continue. Alright, so my super node here, now because I have a voltage source between two general nodes, I have to create a super node, which will be this highlighted area. This highlighted area is my super node. So I write the KCL for this highlighted area. Whatever current enters the boundaries of this area, that would appear in my KCL for the super node. If I closely look at this area, I can see that there is one current is involved here, the other current is this one, the other current is this, and one current is I1. So there are four currents that have to do with this super node. So I write the KCL for the super node, which includes I1, I3, I4, and IX. So let's do that. And also, as I said, my VA is, in this example, VA is what? Is minus 15. Why is it minus 15? I can say, okay, this is 15 volts, which equals the voltage of the node connected to the positive polarity, which is the ground in this case, so it is 0, minus the voltage of the node connected to the negative polarity, VA in this case. So from here my VA will be minus 15 volts. Alright, now I have two unknowns, VB and VC, so I need two equations. The equation number one is the KCL for the super node. If you look at the super node, I1 enters the super node, I3 leaves the super node. So I1 enters positive, I3 leaves negative. I2 is inside the super node, so I don't care. It doesn't appear in my KCL, it is inside, it doesn't go out of the boundaries of the super node. So the super node should include the two adjacent nodes to it. I2 in this case is inside the super node and it doesn't appear in the KCL because it doesn't go out of, it doesn't cross the boundary here. Alright, then I4 leaves the super node and IX leaves the super node too. The next step would be to express all these currents in terms of node voltages. So I1 is this current going from A to B. So because of this direction, it means the polarity is like this. So the current is VA minus VB over 0.5K. VA minus VB over 0.5K. I3 is the current of this resistance here. So it is the voltage across the resistance divided by the resistance. What is the polarity? Because the current is going down, the plus is here, negative is here. So the voltage is VB minus 0. VB minus 0 over 1.5K. I4 is going down from VC down, so the voltage across this resistance is, because the current is going down, this is the polarity, so VC minus 0 over 2K. And the last current IX, which is also leaving the super node because it's going up, so it's basically the voltage of the current of this resistor here. Because the current is going to the left, the polarity will be like this. So its voltage will be the voltage of the positive polarity minus the voltage of the negative polarity, VC minus VA. So we don't be careful about this negative sign here. Then Ix itself is Vc minus Va over 1k. So that concludes my KCL. Alright. So in this KCL, in this equation, I already know VA. So this VA is known here, which is minus 15. VB and VC are unknowns. So I have one equation, two unknowns. I need one more equation. So where do I get this other equation? From the supernode, from this voltage source here. I noticed that this positive terminal is connected to node V, and the negative terminal is connected to node C. So VB minus VC will be 10 volt. Very well, now I have two equations, two unknowns, so I can solve for the unknown node voltages here. So I have all this k's here in the denominator. If I multiply both sides of the equation by 1000, it cancels out all k's and they don't really matter here. So in order to solve this system of equations, again I use this website, Wolfram Alpha. You can use whatever method you'd like. The first equation, VA minus VB over 0.5. So VA minus VB divided by 0.5. I don't include the V here because it confuses the software and it will give me garbage. So VA minus VB over 0.5 minus VB over 1.5 minus VB over 1.5 minus VC over 2 minus C over 2 minus VC minus VA over 1. So I have a minus, then parentheses C minus A minus C minus A parentheses over 1 equals 0. But I also note that I know my VA, this VA and this VA I already know it is minus 15. So in this equation I change this VA to minus 15 and this A to minus 15. So I have another minus here, minus 15 is plus 15. Alright, that's my first equation. And the second equation was VB minus VC is 10. B minus C equals 10. So I solve for this. So here is my solution. VB is minus 7.2, VC is minus 17.2. So VB is minus 7.2 volts and VC is minus 17.2 volts. Just double check, minus 7.2 minus 17.2. Alright. So the initial problem, it was asking for Ix and Vx. If you look at Vx, it's obvious that the negative polarity of Vx is grounded and the positive polarity is Vc. So Vx is basically Vc. How about Ix? Ix here is the current going through this resistor. So it is Vc minus Va over 1k. So Ix is VC, this voltage, minus VA, which is minus 15, over 1K. VC itself is minus 17.2, minus 17.2 volts. So minus 17.2 plus 15 is minus 2.2 milliamp. So it's a negative current. It's totally right. It means the actual physical response of the circuit is 2.2 milliamps is going in the opposite direction. The actual response of the circuit in this branch, 2.2 milliamps, is going in this direction.